Welcome. In this video, we'll be discussing the linear programming formulation of the transportation problem. In a transportation problem, the goal is to produce products at supply locations or origins and transport them to destinations where they are demanded at minimum costs. We will be writing an LP formulation for this transportation matrix. The origins are two plants at Boston and Toronto, with supplies or capacities of 300 and 500 units, while the destinations are three distribution centers with demands of 200, 300, and 250 respectively. The costs of transporting a unit of the product from origins to destinations are seen here. For example, it costs $6 to ship a unit of the product from Boston to distribution center 2. Now let's draw a transportation network for this problem. These circles are called nodes for the origins, or in this case, plants. And these are the nodes for the destinations. Here are the plant capacities and here are the demands at the destinations. Here are the shipping costs from Boston to the distribution centers, and here are the costs from Toronto. The arrows from the origins to destinations are called arcs. Now let's define the decision variables for this LP model. Let XB1 equal the number of units shipped from Boston to DC1, then XB2 from Boston to DC2, and XB3 to DC3. Similarly for Toronto, we can use XT1, XT2, and XT3. The number of decision variables is simply the number of origins multiplied by the number of destinations. In this case, 2 times 3, which equals 6 decision variables. Now suppose I don't like listing every single variable, or maybe I just happen to have too many variables. Then I can use the short form as follows. Let Xij equal the number of units shipped from plant I to DCJ, where I equals B for Boston and T for Toronto, and J equals 1, 2, 3 for DC1, DC2, and DC3 respectively. Next, we can state the objective function. Since the objective function is to minimize cost, we write the objective function as follows. Minimize 5 times the number of units shipped from Boston to DC1 plus 6 times the number of units shipped to DC2 and so on. Note that every single cost is accounted for in the objective function. For the constraints, we need to write 1 for every node. For Boston supply, the total amount shipped to the 3 destination centers cannot exceed Boston's capacity, which is 300. So we write XB1 plus XB2 plus XB3 is less or equal to 300. We do the same for Toronto. XT1 plus XT2 plus XT3 is less than or equal to 500. Note here that total supply exceeds total demand. That is, we will not end up exhausting capacity. And that's why we use the less than or equal sign. For DC1 node, we write XB1 plus XT1 equals 200. Equality is used because we have a demand here that must be met, and we have enough supply to meet it. Similarly for DC2, we have XB2 plus XT2 equals 300, and for DC3, we have XB3 plus XT3 equals 250. For non-negativity, we can either list all the variables and state that each is greater than or equal to 0, or we can simply write Xij is greater or equal to 0 for all I and j. And that's the LP model. Furthermore, let's suppose the cost of producing a unit of the product is $20 in Boston and $18 in Toronto. Then we simply add 20 to the shipping cost per unit of the product from Boston and add 18 to those from Toronto. The objective function is thus updated accordingly. Note here that if total supply were to equal total demand, we could have used equality for all constraints. We refer to that situation as a balanced transportation problem. This problem, however, is an unbalanced transportation example where supply exceeds demand. Moreover, we could also have an unbalanced problem where demand exceeds supply. Consider the following scenario. Suppose demand at distribution center 1 increases to 300 units. Then we have another unbalanced problem with demand exceeding supply. Let's look at 2 ways to handle this. Since demand now exceeds supply by 50 units, one approach is to add a dummy plant and assign it a supply of 50 units. Note that these 50 units do not exist. So their cost per unit is 0 and their shipping cost is also 0 since they're not going to be shipped at all. We can thus modify our model as follows. Add d for dummy in the decision variables. Add the new cost to the objective function. They won't really have an impact on total cost. Next, we add a constraint for the dummy node, and then add the units assumed to be shipped from the dummy to the distribution centers. And again, Xij is non-negative for all I and j. At the end of the day, demand will not be fully satisfied at some of the distribution centers because the dummy supplies don't really exist. Instead of introducing a dummy, let's now look at another formulation method we could apply. Since demand exceeds supply, all available supply will be used up. So we simply change the less than or equal signs here to equal signs. And since demand is not going to be fully met at some of the distribution centers, we change the demand equality signs to less than or equal signs. And the model is again complete. Now, suppose for some reason we're not allowed to ship from Toronto to distribution center 3, maybe because the cost is too high or the destination is too far. One way to address that is to simply remove xt3 from the model. But if your model has too many variables and you don't want to be looking for xt3 all over the place, a better way is to add another constraint to the model that states that xt3 equals 0. And that addresses the issue. And that's LP for transportation problem. Thanks for watching.